So let's do one more example of definite integrals before we get to the really nice fundamental theorem. So here our integrand, the function that we're integrating, is x minus 1. So let's calculate the definite integral from 0 to 2. Now once again, our journey starts by finding our favorite antiderivative, which in my case is the antiderivative with no added constant, simply x squared minus x. And I'm going to take this quantity and I'm going to plug in 0 and I'm going to plug in 2. And I'm going to take the difference of those two outcomes. Now plugging in 2 gives me 2 squared over 2, take away 2. Plugging in 0 gives me nothing because 0 squared over 2 minus negative, so plus a 0. This won't have any impact on the result. So in total, we have 4 over 2 minus 2. In total, 0. Now let us graph the function f of x equals x minus 1, and let's try and figure out how we ended up with this result of 0 for the definite integral. So, to graph x minus 1 linear function, this passes through the point -1 when x is 0, passes through the point 0 when x is 1, and is equal to +1 when x is +1. Now, the first thing that troubles me when I look at something like this is what do they mean when they say the area under the graph of the function f of x? That terminology makes sense when f of x is always above the x-axis, but what about in this case when f of x is below the x-axis at certain points? It would be more accurate to say the area between graph and x-axis. It's really what is being implied with this language in the case that f of x is not an entirely positive function. What is the area between the graph of f of x and the x-axis? But even then, it doesn't make sense to me that that area would equal 0 because we're getting some area from this triangle on the right-hand side, and it looks like we're getting an equal amount of area from this triangle on the left-hand side. So although it seemed in our previous couple of examples that the definite integral always gave you the area under the graph of the function, that held true only in the case that your function was always positive. In the case that your function dips under the x-axis in certain points, the definite integral is giving you a different quantity, which is sometimes called the net area or the signed area. The net area or signed area of a region says, look first at the area of all the regions above the x-axis. Count those as positive. Count those as positive. Then look at the area of all the regions under the x-axis. Area below x-axis. Count those as negative. The net area is the combination of these two. The area above the x-axis counted as positive, and the area under the x-axis counted as negative. So in other words, area above minus area below. That explains why, in the previous exercise, our definite integral worked out to be exactly 0. The area above the x-axis and the area below the x-axis for this function are exactly the same. So if I count the one above as positive and the one below as negative, then those two areas will completely cancel each other out, giving me a definite integral of 0. This relationship between the definite integral and between net area is described by the fundamental theorem of calculus. It says that if you take the definite integral of a function f of x from a to b, the result of this will be the net area between f of x and the x-axis on the interval from your lower limit to your upper limit of integration, the net area between these two. So someone comes to me and they say, calculate the net area between this rational function and the x-axis on the interval from 0 to 3. So let's just do a quick sketch of the situation. The function on the interval 0 to 3 will look a little bit like this, like a rational function shifted to the right and down. So probably slightly like this, I would say. So let's go ahead and calculate that net area using definite integrals. I'll integrate from x equals 1 to x equals 3, 1 over x plus 1 minus 1 dx. So let's come up with our absolute favorite antiderivative. For example, my favorite would be natural log absolute value x plus 1, the antiderivative of this linear in the denominator function, minus x, the antiderivative of 1. Let's plug in 1 and 3 and see what happens when we take the difference. Plug in x equals 3 and we get natural log of 4. Take away 4, take away natural log of 2, plugging in x equals 1, take away negative, so add 1. And so this, simplified, is the exact value of the net area between this graph and the x-axis. Beautiful, beautiful mathematics. Now, what's very nice about this is that if you are lucky and if you have a function that happens to be an odd function, like sine or like x cubed or like cube root of x, and if your upper and lower limits of integration are opposites of each other, you can find the definite integral very, very quickly. An odd function mirrored across the x-axis. If you flip the x values, the y values also flip. So an odd function will look a little bit like this, a, and then on the left-hand side, the mirror image going to negative a. Now, as a result of the function being odd and limits of integration being opposite, you can take negative a to a f of x dx, and the result will always be 0. Because for an odd function, the area on the right-hand side will always cancel out the area on the left-hand side, signed area. But please be careful. This is only true for odd functions. So be careful. If you try and do this for the integral from negative 1 to 1 of something like x squared dx, this is not 0 because x squared is not an odd function. It would only work for something like sine of x, for example, because this function is odd.